Hello students, welcome to our channel. In previous video, we discussed about normed linear space and some examples of normed linear space. In today's video, we will discuss the complete normed linear space which is known as Banach space. Convergent sequence in a normed linear space. Let capital X be any normed linear space and Xn be any sequence in capital X, then the sequence Xn is said to be convergent sequence if there exists X belongs to capital X such that norm of Xn minus X is less than epsilon for every n is greater than or equal to n naught. That is, limit n tends to infinity, Xn is equal to X, or limit n tends to infinity, modulus of Xn minus X is equal to 0. Kochi sequence. Let capital X be any normed space and Xn be any sequence in X, then the sequence Xn is said to be Kochi sequence in X if there exists Mn belongs to capital N such that norm of Xm minus Xn is less than epsilon for every Mn is greater than or equal to n naught, where n naught is any fixed number. Banach space or complete normed space. Let capital X be any normed linear space, then capital X is said to be Banach space or complete normed space if every Kochi sequence in a normed space is convergent sequence. It is complete in the metric induced by the norm of x minus y is equal to distance between x and y. For every x, y belongs to capital X. Now we will discuss some examples of Banach space. Example first. The set of real numbers is a Banach space under the norm defined as norm of x is equal to modulus of x for every x is belongs to R. Solution. First, we shall prove that R is a normed linear space norm of x is equal to modulus of x is greater than equal to 0 for every x is belongs to R, because we know that modulus quantity is always non-negative. Therefore, norm of the number is also non-negative. Let norm of x is equal to 0. This implies modulus of x is equal to 0. This implies x is equal to 0. So, if norm of x is equal to 0, then x must be equal to 0. Conversely, let x is equal to 0, then modulus of x is equal to modulus of 0, which is equal to 0. This implies norm of x is equal to modulus of x is equal to 0. Hence, if x is equal to 0, then norm of x is also equal to 0. Thus, norm of x is equal to 0 if and only if x is equal to 0. Second, let x, y belongs to R. Norm of x plus y is equal to modulus of x plus y, which is less than equal to modulus of x plus modulus of y, which is equal to norm of x plus norm of y. So, triangular inequality property is satisfied. Third, alpha into x its norm, which is equal to alpha x its modulus, which is equal to modulus of alpha into modulus of x, which is equal to modulus of alpha into norm of x. Thus, R satisfies all the properties of normed linear space. Now, we shall show that R is complete, that is, every Kochi sequence is convergent sequence. Let xn be any Kochi sequence in R. So, for given epsilon greater than 0, there exists positive integer n naught such that xn minus xm its modulus is less than epsilon for every n m is greater than equal to n naught. Xn xm belongs to R. Let xm is equal to x belongs to R, then xn minus x its modulus is less than epsilon for every n is greater than equal to n naught. This implies xn converging to x, which is belongs to R. So, the Kochi sequence xn is convergent sequence in R and convergent to x. Thus, R is complete. Hence, R is a complete normed linear space. that is R is a Banach space. Similarly, we can show that the set of complex numbers, that is C, is also a complete normed space, that is C is a Banach space. Next example, show that the Euclidean space Rn is a Banach space. Solution. First, we shall show that Rn is a normed linear space with norm defined as norm of x is equal to summation I varies from 1 to n modulus of xi its square raised to power 1 by 2. This result we already proved in previous video. So for this, please see the previous one. Now we shall prove that Rn is complete normed space. So let x m be any Kochi sequence in Rn. The sequence xm is convergent sequence in Rn. Let xm belongs to Rn, then xm is equal to xi1 m, xi2 m, xi3 m, and so on xi n m. Since Xn is Cauchy sequence in Rn. So for given epsilon greater than 0, there exists positive integer n naught such that norm of x m minus x r is greater than less than epsilon for every m r is greater than equal to n naught. This implies norm of xm minus xr, its square is less than epsilon square for every m r greater than equal to n naught. This implies summation I varies from 1 to n x im minus x ir, its modulus square is less than epsilon square. This implies modulus of xi m minus xi r is less than epsilon square. This implies modulus of xi m minus xi r is less than epsilon for each I is equal to 1, 2, 3 up to n. This shows that for each I varies from 1 to n, the sequence xi m is a Cauchy sequence in R, but we know that R is a complete normed space. So xi m is convergent in R, that is xi m converging to xi I varies from 1 to n. As m tends to infinity, that is xi 1m converging to xi1, xi2m converging to xi2, xi3m converging to xi3, and so on. This implies xm is equal to xi m1, xi m2, xi m3, and so on, converging to xi1, xi2, and so on. Let xi1, xi2, xi3 is equal to x, which is belongs to Rn, then the sequence xm converging to x belongs to Rm, Rn, that is Rn is complete normed space, that is Rn is a Banach space. This space Rn is called Euclidean normed space or Euclidean Banach space. Similarly, we can prove that Cn is also a Banach space which is known as unitary Banach space.